Hello, this is Colin Goebel. The purpose of this video is to illustrate some more of the concepts of how to convert decimal integers into binary. Binary arithmetic, base 2 arithmetic, as I'm sure you're aware, is the basic standard that digital computers use to store numbers. Why do they use binary arithmetic? Because in the world of electronics, circuits can be either on or off. A circuit, like a light bulb, which is in the on state, represents the number 1, and a circuit which is off, like a light in the off state, represents the number 0. So computers do all of their arithmetic to base 2, and the question is, how do we convert the normal human decimal arithmetic into the computer's binary notation? Now, in general, most computers allocate at least 32 digits, or bits as they're known. The word bit stands for binary digit, either 0, 1, or 1, or even as many as 64 bits, or on some very large computers, even 128 bits. But in this particular example and discussion, I'm going to assume that integers are going to be stored in 8-bit quantities. I'm going to store an integer in an 8-bit byte. The reason for this is I don't want to have to do all of the arithmetic using 32 bits or 64 bits, because it will add a great deal of typing and won't particularly add anything to your understanding of the discussion. So for the purpose of this example, as I said, I'm going to assume that we're going to allocate 8 bits, or 1 byte, for each integer. But please remember, in the real world, it's going to certainly be 32 bits per integer, or even 64 bits. Okay, so if I have 8 bits at my disposal, and I need to store positive and negative numbers, I somehow need to store the sign bit encoded in those 8 bits. And the way that's done is the computer takes the leftmost bit, this bit right here, the left of those 8 bits, and interprets that as a sign bit. So quite simply, if the leftmost bit is set to 0, the circuit's off. That's treated as a positive number. And if the leftmost bit is 1, the circuit's on. That's treated as a negative number. Very simple. The leftmost bit, the most significant digit, is simply a sign bit. So obviously the smallest possible number that we can store that's positive is a set of 8 0 bits. 0, the leftmost 0, because the number is positive, and the remaining 7 bits indicate that the value of the number, the absolute value of the number, is 0. So our smallest positive, or non-negative number, perhaps I should say, is plus 0. In fact, let me make that clear. This is the number 0. And I'll say the smallest non-negative number. Let's write that. Okay, that's 0. All the bits are set to 0. Now the largest possible positive number is 127. Why? Well, it's a positive number, so the sign bit has to be set to 0. I can set all of the other bits to 1. And if we do the math, we'll find that 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 gives us a grand total of 127. Remember that in binary arithmetic, each column represents a factor of 2 more than the column to the right. In decimal arithmetic, of course, it goes 1, 10, 100, 1,000, 10,000. But here it goes 1, 2, 4, 8, 16, 32, and 64. Okay, the largest possible positive number, therefore, in an 8-bit quantity is 127. Now, negative numbers are a little bit tricky. The obvious answer that you might think towards storing a number such as minus 5 is just to calculate plus 5 as we did, well, I guess we didn't, but we'll do that in a moment when we do the example. We could calculate the positive value of a number and then just set the sign bit to minus to indicate that the number is negative. However, that's not the way it's done in computers, and let me explain one reason why. because it is the obvious way to think about doing it. If 0, 0, 0, 0, 0, 0, in other words, if all zeros represents the number plus 0, and we just change the sign bit, then minus 0, of course, would be 1 followed by 7 zeros. Let me say that again. That would be minus 0. This number is plus 0. Now, mathematically, minus 0 should equal plus 0. They're the same thing mathematically. And yet that bit pattern is not the same thing as that bit pattern. So, for reasons associated with that kind of analysis, negative numbers are stored in a more complicated notation known as 2's complement. Let's take a look at how that works. First of all, the rule is if you want to convert a negative number to its binary equivalent, you first convert the positive equivalent to the number. So if you're trying to convert minus 5, say, the first thing you do is convert the number plus 5. The next step is to invert all the bits, including the sign bit. Just change every 0 to a 1 and every 1 to a 0. And then you add 1. And if you follow that procedure, you wind up with minus the negative number in 2's complement notation. Let's take an example. Let's try and work through minus 5. First, we're going to convert plus 5 to 8-bit binary. The sign bit is 0 because it's a positive number. The other less significant digits are 1, 0, 1. Why? Because 5 is 4 plus 1. There's 1, 4, no 2's, and 1, 1. 4 and 1 is 5. That is plus 5 in 8-bit binary. Okay, the next rule is we invert all the bits. We convert every 0 to a 1 and every 1 to a 0. That gives us this number. And then finally, we take this number and add 1. In this case, it's easy to add 1. We don't have any carrying to do. So we add 1. I get 1, 1, 1, 1, 1, 0, 1, and then the 1 that we've added in there, 0, 1, 1. So this is the number here. So this is quite simply the 8-bit 2's complement representation of the number minus 5. It's the final answer to this example. Okay, as a final math note on this, just note that plus 5, which was this, if I add it to minus 5, let's try and do the arithmetic. 1 and 1 is 0, carry 1. 1 and 1 and 0 is 0, carry 1. 1 and 1 and 0 is 0, carry 1. 1 and 1 and 0 is 0, carry 1. And if you work it all out, you'll discover that minus 5 plus 5 plus minus 5, if we add this number to this number and carry all the way across, we wind up with all zeros, which is 0, which is what we would want. We would want plus 5 plus minus 5 to come out to 0. The math of this is quite complicated, but the rule here is quite simple. And I'll just go through that again. Convert the positive equivalent of the number to binary, then invert all the bits, including the sign bit, and then add 1. That's it. Thank you very much.